Hi Physics 30. Today I'm making a video about moving charges. So we know that a moving charge produces a circular magnetic field. Think back to Hans Ørsted noticing that current in a wire deflected a compass needle. To predict the direction of a magnetic field produced by a moving charge, you use the same hand rule we saw for current in a wire. The only difference being you may have to use your right hand. If the moving charge is positive, you will use your right hand. So I've given an example here. So just review. The charge is moving to the right. I place my thumb in that direction, and then my fingers curl in the direction of the magnetic field. Okay, so they curl below the wire, coming out of the page, and then down in front of the wire, and then into the page below, and then up behind. All right, so since the charge produces a magnetic field when it's moving, when entering another magnetic field, like between magnets, it will be acted on by a magnetic force. Two magnetic fields produce a magnetic force. The direction of the magnetic force on a moving charge is determined by this hand rule. As always, use your left hand when considering negative charges and your right hand for positive charges. You use a flat hand. The thumb is the direction the charge is moving in. Your fingers are the direction of the external magnetic field. So just a reminder, that's away from north towards south. Then your palm will face in the direction of the magnetic force. So I've got a quick example here. It's a negative charge, so I use my left hand. My thumb has to be pointing down, and my fingers have to point north to south. So it's my left hand, thumb down, my fingers are going north to south. My palm, you can't see it because it's facing toward the page. That means that this negative charge will be deflected into the page. Okay, so this negative charge would be coming down, and then it would turn into the page as it got between these magnets. To calculate how much force acts on a charge in a magnetic field, you use QVB. V is the perpendicular speed, or the component of velocity perpendicular to the magnetic field. If it's not perpendicular, which will only happen rarely, you just introduce a sine theta term. Okay. Now, since the magnetic force acts on the perpendicular velocity and it deflects the charge perpendicularly, there are two consequences of that. The first one's the main one. It deflects a charge in a circular arc. That means that the force is centripetal. So this will be from Physics 20. You'll remember a centripetal force is mv squared over r. We're going to use this technique a lot, where we say magnetic force is centripetal. So QVB equals mv squared over r. There will be an example later in this video. The second consequence may come up on a test. It's good to know, but I haven't seen it on the diploma exam more than once. It's that magnetic forces, it's true of any centripetal force, they don't do any work. Okay, that'll be a bigger deal if you continue on with physics. There's not much we do with that factoid in Physics 30. Now let's talk about a charge entering a relatively large magnetic field. All right. Oops. Now it may not be clear, but I've tried to write it down. The magnetic field here is directed into the page. So those are circles with X's. Okay. So that would be like if there is a north pole above the page, a south pole below the page. Now we have to use a hand rule to determine how this negative charge will be deflected. So it's negative, again I'll use my left hand. My thumb has to point to the right, because that's the way the charge is moving. But this time the field's into the page, so my fingers have to go into the page. Okay, if my thumb is to the right and my fingers are into the page, my palm is facing down. So check this out. This negative charge, it's going to cruise in, but it'll be deflected down. Okay? But the reason I've asked us to consider a large magnetic field is that as it's traveling down, it's still stuck in it. So now consider this negative charge moving down. My thumb will have to point down. My fingers are still into the page. And now my palm's facing to the left. So this guy is going to be deflected to the left. Let's do the same thing. Now my palm has to face, my thumb has to face to the left. My fingers are still into the page. Hard to tell. Try it yourself, but now my palm was facing up. Okay. And I think you can probably see what's going to happen now. If my thumb faces up or points up, my finger's still into the page. Now my palm's facing right. What we can actually do is trap a charge in a magnetic field. Right, and this again is more or less proof that the force is centripetal. Okay, that it causes the charge to just move in a circle. If the field is large enough, you can keep that charge moving in a circle. Okay, so here's an example. I'm saying an alpha particle enters this field. There's the magnitude of the field, 20 milliteslas, speed 5 × 10⁶ meters per second. This is a really common question that you'll definitely have to do on any test. Find the radius of the path of deflection. Okay? What we're going to do is that thing I showed you just a minute ago. We know that the magnetic force is centripetal. Okay? 99 times out of 100, the charge enters perpendicularly. Here the field's coming out of the page, right? That's 90 degrees to anything moving to the right, actually anything moving on the plane of this paper. Within the formula, one of the V's cancels out. We're looking for R, so I'll just shuffle this around a bit. Ends up being mv over qb. Okay, mass of an alpha is on your formula sheet. V is given up there as 5 × 10⁶. Q is double the elementary charge, also on your formula sheet. And then the field was 20 milliteslas, which is 10 to the -3. All right, so I popped everything in my calculator here. I got 5.195. I'm going to call that 5.2. And base units, so it's going to come out in meters. Okay, so that's the most common type of problem that you'll have to solve involving charges moving into a magnetic field. Okay, there are a couple more things I want to tell you. charges moving parallel to magnetic field lines. So that would be like moving something horizontally if the magnets are aligned horizontally. They experience no magnetic force. Okay, they're moving along field lines. It's only when they cut the field lines is there a force. You can see that mathematically though. If you're moving parallel, you're either 0 or 180 degrees. Sine of 0 and 180 degrees equals 0. So you'll get a force of 0. I don't know if this will come up ever in the course, but it's good to know and interesting to think about. Charges entering a field at a different angle, so not 0, not 90. Their perpendicular velocity is deflected circularly by the field, or by the magnetic force, okay? But their parallel velocity is undisturbed, kind of like a 2D projectile. So the result, I don't think my picture is great, but the component of velocity that's parallel to these magnets stays constant. And what happens is there's a circular deflection as it goes through. Okay. And if you just imagine, or you trace my pen getting circular deflection, but maintaining a horizontal velocity, you call that a helix. All right. It's kind of like a screw shape, but screws get tighter at the bottom. A helix is like a constant circle moving through space. Okay. That's it.